Okay, so today we're going to see the NeuralReality³ AI engine parameters. So, in order to do that, we have to go into the Play Now menu, and select the NeuralReality³ AI item option. Once the interface is loaded, we can now scroll down and see the various controls we have here. So, you'll have to choose your favorite lottery first. For that, we need to select the region, the country, the jurisdiction, and, of course, the lottery. So, first I'm going to choose the region. So I'm going to go ahead and choose North America. I'll now go to country, and I'm going to select the United States. Then to the jurisdiction, state, district, etc. And I'm going to select District of Columbia as an example. And then we'll get a list of lotteries available. In this example, I'm going to select the Mega Millions lottery. We now get a lottery type description. In this case, 5 out of 70 plus 1 out of 25. What this means is that, in order to win the jackpot, we have to hit 5 numbers out of a pool of 70, and 1 bonus number out of a pool of 25. We can also see the last drawing, in this example, stored within Neural-Lotto's databases, and the price to run the prediction. The first part of the hyperparameters section is the learning rate setting. The learning rate determines the magnitude of the adjustments made to the AI model's parameters during training in response to the calculated error or loss. It controls the step size taken towards minimizing the loss function through optimization algorithms, like gradient descent. It's important to note here that, while it accelerates the convergence of the model to a solution, a too high setting risks overshooting the optimum, leading to instability. Conversely, a lower rate may result in slower convergence, but offer stability and precision. So, for those of us who are into neural networks, we should strive to select a value which represents a balance between speed and precision. In this case, I'll go ahead and select a central, or midway, value. Please note that the default value is always a good starting point. The next hyperparameter is the history setting. The history determines how many lottery data points are used to generate a prediction. In spite of how many drawings, or data points, the system has available, emphasis is placed on the last data points specified in the history setting, which ranges from 10 to 500. If the value exceeds the total amount of data points for a given lottery, for example, a newly instituted lottery, only the maximum actual data points available are used. So, as an example, if there are only 50 historic drawings in the newly created lottery, and I select 500, the system will only use up to the maximum available, 50 in this case. If it has more than 500 available data points, it will place emphasis on the last 500. In this example, I will choose the last 150 historic data points. The next setting is epochs. Epochs determines the number of times the entire training dataset is processed by the AI model during the training phase. It is akin to saying, how many cycles? Each epoch consists of multiple iterations, where the model sequentially processes batches of training examples, adjusts its parameters based on the calculated error or loss, and updates its internal representations to better approximate the underlying data distribution. The default value is 8,500. It ranges from as low as 100 to as much as 50,000. As usual, the default value is the best place to start, so I'll just leave it there. It is a good starting point, as it also provides the best balance between speed and overfitting. Next is stepping. Stepping specifies the number of historical blocks utilized for training through a decremental process, commonly known as backstepping. So, stepping and backstepping is, basically, the same. For instance, if the value of stepping is set to 10, and history is 100, then the training involves 10 decremental cycles, or steps, per epoch. So, what you're doing here is basically multiplying epochs times stepping, or 50 in this case. But if I set it to 0, the parameter is unused. A good starting point is somewhere near the default. Next is momentum. Momentum determines how much inertia, or persistence, of the gradient descent, or other optimization algorithms, is used, allowing it to continue in the direction of previous updates, with a certain momentum factor. It can be described as a method that accelerates convergence, by accumulating a fraction of the past gradient updates. With a value of 0, the effect is that the gradient updates contribute very little to the current update direction. Conversely, a value of 1 can accelerate convergence, but it tends to overshoot and does not usually ensure stable and effective training. So, careful tuning of this parameter is advised. The next hyperparameter is neurons per layer. This parameter determines how many computational units, or nodes, are present within each layer of the network architecture. These neurons are responsible for processing input data, applying transformational operations, and propagating information through the network. Now, this is per layer, so this will basically get multiplied by this one. So, right here, I'm actually having 1,000 neurons per layer times 500 layers, which gets me 500,000 neurons created, right here. You should try not to go all the way up to the maximum, because that will create a large amount of neurons for each level, which is usually too much. The default values are usually good starting points to create very high performance, balanced networks. The next hyperparameter is, precisely, layers. It determines how many structural components that organize and process information are created within the AI model. So, we have neurons times layers. The default value of 500 is a great starting point. You can go all the way up to 3,000, or as little as 10. 10 times 10 will result in a small, 100 neuron network. Very deep neural networks are not always better, so you should start with the layers value somewhere around the default, and go from there. Next up is the perceptron's hyperparameter. This setting is actually a range, spanning from 10,000 to 50,000. Values can be overlapped, creating a single value instead of a range. For example, 20,000 or 35,000, instead of 20,000 to 35,000. Perceptrons determines the range of auxiliary, multi-layer simple binary classifiers that are created. Perceptrons serve as fundamental building blocks in neural networks by processing input signals and applying weights to produce output, forming the basis for complex decision-making and pattern recognition tasks. They learn nonlinear relationships by adjusting their weights based on observed error during training, with the aim of correctly classifying input data into predefined categories. As usual, a medium-sized network is both fast and precise. Next is the algorithm hyperparameter. The NeuralReality³ AI engine has 25 different, highly adaptive, fuzzy logic learning algorithms at its disposal. There are no hard and fast rules as to which algorithm is better for a given lottery, so experimentation is advised. Careful observation of results should be exercised with each algorithm lottery pair, as they provide different computational techniques and methodologies used for forecasting and prediction. The next hyperparameter is continuous time. CTNNs are a class of neural network models that operate on continuous timescales, in contrast to discrete time models, like traditional feed-forward or recurrent neural networks. This hyperparameter is optional, meaning that we can activate it or not. It's off by default. If we turn it on, we'll get two additional neural network hyperparameters. The first one is Grossberg neural networks. It determines how many adaptive resonance theory neural networks are created within the main, deep neural network. We have from 1 to 32. The default, if on, is 5, so it's a good starting point. The next one is neocognitron neural networks. While they are not continuous time neural networks per se, but instead a type of self-organizing network, they have been successfully coupled to adaptive resonance theory networks to provide for exceptional pattern recognition tasks, as is the implementation here. So here, if enabled, we can select how many neocognitron NNs, from 1 to 16, are created. 4, the default, is a good starting point. So, as stated earlier, the default is off, so I'm just going to leave this off. The next hyperparameter is self-organizing hybrids. Self-organizing hybrid networks are a class of artificial neural networks that possess the ability to autonomously organize and adapt to the structure of input data without explicit supervision. The default is off. We can turn it on, and we'll get two types of self-organizing maps. The first one specifies Cohonen self-organizing maps. We have from 1 to 96, so we can specify how many we want. If enabled, we can also specify how many Hopfield recurrent neural networks are created. They are a type of recurrent neural network that are characterized by their ability to store and recall patterns or associative memories. We can choose from 1 to 96, the default being 40. They both work together if the self-organizing hybrid switch is turned on. The default is off. The next hyperparameter determines if probabilistic neural networks are included in the AI model. They are also known as probabilistic graphical models. They are a class of graphical models used to represent and reason about uncertainty in complex systems. Once again, the default is off, but we can turn it on, at which point we'll get two additional hyperparameters. One is, of course, probabilistic neural networks. We can specify how many auxiliary PNNs are created, from 1 to 48, if the switch is on. 12 is the default. In the same way, we can choose how many auxiliary Bayesian neural networks are employed. Bayesian neural networks treat model parameters as probability distributions, allowing for the quantification of uncertainty in predictions. The default is 8. We can create from 1 to 48 if, of course, the probabilistic switch is on. The default is off, so I'll just leave it off here. The next hyperparameter is the best first search toggle switch. Best first search is a graph traversal algorithm that explores a search space by prioritizing nodes based on a heuristic function. The default is off, but you can turn it on, which the model now employs on a need-to-use basis. I'll just leave it off for now. The next hyperparameter is the breadth first search toggle switch. It's also a switch, just like this one. It's either off or on. It is also a graph traverse algorithm that systematically explores a graph by visiting all the nodes at a given level before moving on to the nodes at the next level. It's optional. It has been proven very useful in some lottery dataset scenarios, not all of them. So, the default, once again, is off. Next is the depth first search hyperparameter toggle switch, or DFS. It is a graph traversal algorithm that systematically explores a search space by prioritizing the exploration of paths as deeply as possible before backtracking. The default is off. We can, of course, turn it on or off. All of these toggle switch hyperparameters are optional, which the system may employ on a need-to-use basis if activated. Next is the uniform cost search, or UCS, toggle switch. It is also a graph traversal algorithm that explores a search space by systematically expanding nodes with the lowest cumulative cost from the start node. Unlike the breadth first search algorithm, which prioritizes nodes based on their depth from the root, UCS considers the cost associated with reaching each node. Try to think about that for just a moment. So, we can turn it on, along with this one, although uniform cost search will tend to budgetize, which the breadth first search algorithm won't, by prioritizing cost. The default is off. They won't fight each other, but instead collaborate as needed. Next comes the means-ends analysis hyperparameter toggle switch. It's off, by default. It is a problem-solving strategy that involves breaking down a problem into subgoals and systematically reducing the difference between the current state and the desired state by selecting and applying appropriate operators. It's optional, and the default is off, but we can turn it on. And then we have another toggle switch, non-monotonic reasoning. This switch, which is off by default. It is a form of reasoning in artificial intelligence and logic that allows for the revision of conclusions or beliefs in light of new information or evidence. The decision to use non-monotonic reasoning here would be driven by the need to allow flexible adaptation to changing or uncertain lottery dataset behavior, but should not be used if computational complexity or the need for clear decision-making outweighs the benefits of dynamic reasoning. Next is the Dempster-Shafer functions hyperparameter, which ranges from 1 to 14. It is a range, the default being from 3 to 6. It determines the range of mathematical framework reasoning belief functions that are created, and employed during the construction and operation of the neural network. Dempster-Shafer theory is particularly useful in aggregating evidence from multiple sources that may be incomplete or conflicting, while non-monotonic reasoning is adept at revising conclusions based on new evidence or context changes. Means-ends analysis uses this information to make informed decisions and systematically move towards a goal, so all three are complementary. However, the real tight-knit performance implementation occurs with these two. Finally, the last hyperparameter is wheeling. This switch is only available to lotteries which do not allow repeating numbers. For example, in this lottery, we have 5 non-repeating numbers from a pool of 70, notwithstanding the bonus number. So the wheeling toggle switch enables the system to output a greater quantity of numbers than the base, or standard, quantity of picks allowed. In this case, 5. So, for example, if you have your own lottery combinatorial wheel or program, you can feed the output of the system into your own wheel, so as to generate various directly playable combinations, with which you can span a greater number of numbers, thus promoting more hits or prizes within those different combinations. If available and activated, we now have the base numbers plus 1, 6 to 12, in this case, from which we can choose. As an example, in a 649 lottery, we can specify an output of 7 or more numbers, instead of the standard 6. Since we selected the Mega Millions lottery, which has 5 pick numbers, the system allows from 6 to 12 in this case. So, you can select more than 5 if you want. It's off by default, and is enabled only for select lotteries. At the bottom is a display field, which shows the investment necessary to run the system. For that, you need to select an available promo code to cover this cost from the drop-down list. Now, the drop-down list will not show any promo codes if you are not logged in. However, if you are logged in, the drop-down will show a list of your purchased promo codes, including total and remaining uses, and expiration date, with which to cover this cost. And after that, you can submit the request, after you have selected a code. So, that's all for today's tutorial, which covers the basics of how to use the NeuralReality³ AI engine interface hyperparameters. Until next time.